Yihua's main talk on the big LMCache architectural change. On the MP mode design, I will give a brief open source report. So about the status of LMCache, I guess between the last office hours and today's office hours. And so the main things that are happening, without getting into too many details, what's exciting first is the Q2 roadmap. So on the Q2 roadmap, there's a lot of details on what PRs or features need to be built this quarter that open source contributors please check out if you're interested in contributing. Some main things that are happening are the LMCache CLI. So in the future, if you're on a Mac or Windows without a GPU, you should be able to use the LMCache CLI and connect to the LMCache server and be able to talk to the 𝐾𝐽 layer of your cluster. So that's an expansion in, I guess, the LMCache interface. What's also kind of exciting is we're trying to branch out into more serving engines and integrations. So last quarter, in quarter one, we did a lot of new integrations with storage backends, CXL. We started doing some better SSD integration, but this quarter we're also focusing on expanding upward with projects like VLM Omni, TRT LLM. And lastly, a feature a lot of people have been asking for, especially storage vendors, is good 𝐝𝐞 quantization and compression. So that will be a native interface to LMCache. So all the sort of research and optimizations done around this ecosystem, they'll be able to plug right into LMCache, and compression, 𝐝𝐞 compression will be native. So yeah, that's about it for the high-level overview of what's happening.
So Yihua, if you want to start now sharing your slide.
Sure. All right. First of all, thanks, Sam, for the introduction, and very excited to see there's a lot of new updates and progress in LMCache. And today, what I'm going to talk about is very exciting new things, new architecture of LMCache is what we call it, the LMCache MP mode. So the MP mode at a very high level, we treat it as basically a disaggregated AI native data plan, which means that you can separate your 𝐾𝐽 cache management totally external to the serving engine. And let me tell you more details during the talk. And by the way, I'm Yihua. I'm probably you guys already have seen me or know me, but I'm the CTO at Tensormesh. Also, I'm one of the core maintainers at LMCache. So today, I think many people realize that 𝐾𝐽 cache becomes more and more important, and also people realize that the 𝐾𝐽 cache is actually the key to make the LM inference more efficient. So as just a very quick background, 𝐾𝐽 cache is basically a big tensor, big data that is generated by LM and captures the model's understanding of the input context. And by store and reuse or probably manipulate the 𝐾𝐽 cache, what you can get is you can actually cut your GPU cost and reduce the request latency, because you're skipping a lot of very expensive attention computing. And also you will have a better scalability when you deploy your model into the production cluster, because you can avoid a lot of redundant computation by reusing the 𝐾𝐽 cache. So I think it's more and more people start to realize this, and it's becoming a very trending topic in the community. And as what I just said, people want to do more and more things on 𝐾𝐽 cache to improve inference. So there are many different cool ideas emerging every day. So for example, people want to save their 𝐾𝐽 caches to remote storage because you realize, okay, the GPU is not enough and the CPU memory is not enough. So probably they want to store it in a larger capacity and cheaper storage. And also people may want to observe the 𝐾𝐽 cache life cycle. So previously there's a key metric, we call it 𝐾𝐽 cache hit rate, but recently people will go beyond just the KV cache hit rate. For example, they want to know, okay, how long does this KV cache stay in GPU memory before it's evicted? Or how long did it stay in like CPU memory before it's evicted? So those kind of metrics can help people better understand their KV cache service better and improve their production service. And also, people may want to share KV cache across different serving engines. Like it's not only about PD disaggregation, it's also about like reuse KV cache across the whole cluster, or maybe across even different serving engines, like maybe let VRM do the preview and let SGDOM do the decode. And finally, there's a lot of like more researchy topics. For example, KV cache compression. You know, probably everyone knows that turbo quant is become super hot since last week, and many people are getting to know, okay, probably we can do more on updating the KV cache to make the inference become better. However, now here's a however. However, if we want to do a lot of things on KV cache, we started to find, or people started to find, it's pretty painful. It's pretty hard to do it inside those LM inference engines. So there are a few like examples. So first of all, if you want to do a lot of KV cache operations, you want to do the monitoring, you want to do the update, it actually incurs a lot of overhead in inference. So for example, like we do see there's peers implementing turbo quant in VRM and SGDOM. However, it actually slows down the LM inference by 20% or even more, and the TTFD you got double TTFD when you employ this turbo quant implementation. So there's a significant overhead actually. And secondly, it's like the serving engine is super difficult to hack and to make modifications. So like there are two levels. I will also explain with an example. You know, recently there's a very new paper called Try Attention, which basically is also doing a bunch of super amazing KV cache work, and they have open sourced their code. And I took a look. It's pretty impressive, but it does a lot of changes in the inference engine in VRM. So it did a lot of monkey patches. And also, some of the monkey patches, they're not using a stable interface inside VRM, which means when VRM upgrades its version, those interfaces will break. So, which will make the KV cache optimizations become now not workable. And also, inside the serving engine, the interface for you to do the KV cache operations is so limited. You cannot do it freely as you want. You probably, the only thing you can do is you can save it to some kind of storage and load it when needed. But actually, people want to do more and more on the KV cache based on their needs. So there are lots of problems like this. We started to think about, okay, what's the best way to address those problems? And our insight, it's actually not our insight, but following this line of thought, it will be pretty natural to think about, okay, how about we just separate the KV cache management from the serving engine? So basically have a unified or have a totally separated service in the system, just focusing on the KV cache. And that is why we built this MCache multiprocess mode. So to give it, to explain it a little bit more, what does this separate KV cache management really means? So before MCache MP mode, I would say almost all the existing KV cache libraries or KV cache systems, they do share a common characteristic. Is basically running within the serving engine as a library. So like there's some XX store or XX KV or XX management, those kind of libraries, they all run inside the serving engine process. And by separating, by this, what we do for the MCache MP mode is that we run the KV cache management process as a separated entity, as a separated process that is excluded from the VRM process. And VRM process, they're connecting to this KV cache service and talking to it via some long-running connections. So at this stage, you probably will have a lot of questions like, how does it work, or how can it be performant? And I will talk about a lot of things behind this MP modes architecture in the rest part of my talk. And just also feel free to leave your questions if you have any, and I will probably try to answer those questions between those sections. But the remaining of my talk will have the following items. First of all, this is a little bit technical explanation about what is the 𝐿MCache multiprocess mode and how does it work? Like, how does it really work? How does it achieve better performance? And second, I will going through a list of very interesting or very cool features enabled by employing this multiprocess architecture. And the third thing, which is also important, is like, how do we really, how does this MP mode help the production deployment and maintenance? And finally, I'm going to talk about a few things about the vision of the 𝐿MCache project, long-term vision of 𝐿MCache project. So at a very high level, the 𝐿MCache MP mode is something like we are building a disaggregated and distributed KV cache plan. So you can imagine 𝐿MCache MP mode or 𝐿MCache MP data plan as a distributed data box. And applications like serving engines, they're talking to this data box by by reading or writing KV caches that is keyed by the request tokens. And it's actually not only serving engine. Serving engine is pretty clear that they want to store, offload, or load KV cache back and forth. But there's also a lot of like smart algorithms, like just like what I mentioned, TurboQuant. They also basically what they're doing is also read and write, or probably update the KV cache keyed by the tokens. So that's so from the serving engine's perspective, 𝐿MCache is just a box that contains tons of KV caches. And inside 𝐿MCache, inside this 𝐿MCache MP data plan, underneath that, there is actually a distributed architecture where on each node, there is a node local storage manager that contains this local CPU buffer, the local storage, and last month, like Bolong gave us a very cool like presentation about the P2P, which is using RDMA to connect all those CPU buffers so that different nodes can share KV cache across the cluster. And also inside the data plan, there is also a remote share storage where every storage manager can read from or write to. So that's a high-level overview of this MP mode architecture. And now I will go into zoom in a little bit on this integration with the serving engine. How does 𝐿MCache really talk to the serving engine? So by zooming in into a single node, the 𝐿MCache MP process is actually runs as a separate daemon process on every physical server, on each physical server. And when we launch different VM process on that physical server, multiple VM workers, they could be from different TP workers or different DP workers or even different instances or maybe SC-long, will talk to 𝐿MCache daemon process via this long-running 𝐝𝐞 sockets. So every time the VM wants to offload some KV cache into 𝐿MCache, they will just send a request to this input socket, and 𝐿MCache will take this request, process it in 𝐿MCache daemon in this worker thread pool, and after it's done, it will put the return value, return back the return value to the VM process via this output socket. So at this stage, you're wondering like how to, since we are separating the process, since we're separating 𝐿MCache from VM, how do we transfer KV cache across different processes? Because it's like intuitively, it sounds like a lot of overhead to do like IPC transfer across different processes. And also KV cache is super big, so probably that will take a lot of overhead. And we actually address this problem by doing the GPU IPC. So during the initialization, the VRAM process will register the IPC pointer for GPU cache inside LMCache process. So inside the LMCache process, after we see this registration, we are actually building up this shadow GPU KV cache, which is which enables LMCache to read from or write to the VRAM's GPU memory space directly. And during the runtime, when VRAM wants to store or wants to load KV caches from LMCache, they will just send the block IDs over this VMQ socket. So block IDs will be super small, and the real like device to host or host to device transfer actually happens just within the LMCache process. So by doing this, we are actually avoiding the expensive IPC data transfer across the process boundary. So all the KV cache transfer actually happens inside the LMCache. And what's more is like, because we're separating the LMCache process from the VRAM process, this KV cache transfer is totally invisible from VRAM, and it will make just zero overhead to the VRAM inference process. And that is how the LMCache MP mode like internally works. And by having this multi-process architecture, we actually will have a lot of new benefits. Like first of all, we will enable better performance because we are actually doing much less overhead inside VRAM, and also by separating this MP process, it actually allows user to plug in a lot of new logics without considering or without worrying about what if this logic was slowing down the serving engine's inference. And also it will become more manageable because right now you're managing the KV cache as a totally separate service in your system. It's totally decoupled from the serving engines. And I will explain those 3 points in detail when talking about the features. So yeah, are there any questions so far? Because I cannot see the text, see the chat. But if there's no questions, I will just move on to the features part.
No, there is no question so far. At least not in the chat.
So the next thing is about the key features that is enabled by the LMCache multiprocess mode. So the first thing, as I mentioned just now, is by separating the process, we are actually minimizing the impact of this KV cache management operations to the serving engine. So as you may all know, Python is many people know that Python's performance is not good, partly because there is a global interpreter log, or aka the GEO, that if we want to do things like multi-threading things, different threads will have contention on this GEO and slowing down other threads. And in the other KV cache framework, since they're running as a library inside the serving engine, this Python GIL contention will slow down the AM inference, both AM inference and IO speed. And in LMCache MP mode, since we're doing the process level separation, no matter what you want to do in this LMCache process, it does not impact the serving engine at all. So there's like almost zero overhead in the when doing this KV cache offloading, unloading, and other like operations. And also, since if you're putting the KV cache library inside the inside of the serving engine, you will have the limited IO concurrency because like AM worker, it makes a lot of constraints on what you can do. And if you want to do IO operation on SSDs or other things, the IO concurrency will be very limited. However, if we're doing like IO operations in this LMCache MP process, it can be it won't be impacted by the serving engine process at all, and you can get a much more a much higher concurrency and faster I/O operations. So this is one benefit. Another benefit, or another very cool feature is what we call this zero copy CPU sharing. So let's go back to probably 1.5 years ago when we first released LMCache. In the very first release, we actually have this called 𝐝𝐞 𝐬𝐢𝐠𝐴 sharing mechanism enabled by running a remote 𝐝𝐞 𝐬𝐢𝐠𝐴 pool. And by then, if we want to share 𝐝𝐞 𝐬𝐢𝐠𝐴 across 2 VM inference engines, we will first offload the 𝐝𝐞 𝐬𝐢𝐠𝐴 to local CPU, and then send the 𝐝𝐞 𝐬𝐢𝐠𝐴 to the remote pool, and then on the other side, it loads back to the local CPU and loads back to the GPU. So there are actually like 2 extra copies. And recently, like late last year, we have this LMCache P2P mode, which allows different LMCache instances directly sending and receiving data across the CPU. So in that case, if we want to share a 𝐝𝐞 𝐬𝐢𝐠𝐴 from GPU A to GPU B, it will first go to local CPU A and send to local CPU B, and finally push back to local to GPU B. And you can see that there's still an extra copy between CPU A and CPU B. And by using this MP mode, things will get actually very simple. The GPU A will directly write to this shared CPU pool, and since this is on the same node, it's actually a single CPU pool. So the GPU B can directly read from that CPU pool without doing extra sending or receiving. So there is no extra copies. And to give you to put it into this context, like why is it useful? There's a very concrete use case for this feature, which is DPEP serving. So MOE models, they're becoming more and more popular these days, like DeepSeek models or latest Quinn models. Almost all of these models are MOE. And a very important new serving technique is called the data parallel, or the DP serving, which can significantly boost the MOE's models throughput. And the key characteristic is that when we are doing data parallel, actually each data parallel rank, it's the independent engine. It's the independent serving engine instance. And if we can only do this in-process offload, each DP rank will have its own like 𝐝𝐞 𝐬𝐢𝐠𝐴 pool, and those 𝐝𝐞 𝐬𝐢𝐠𝐴 pool cannot talk to each other or have to do the copy, have to do the IPC transmissions to send or receive the 𝐝𝐞 𝐬𝐢𝐠𝐴 across different 𝐝𝐞 𝐬𝐢𝐠𝐴 pools. But the LMCache MP mode, we're actually unifying the 𝐝𝐞 𝐬𝐢𝐠𝐴 pool on the single DRAM, so that when different DP ranks access this 𝐝𝐞 𝐬𝐢𝐠𝐴 pool, there's no need to copy or to share or to send or receive the 𝐝𝐞 𝐬𝐢𝐠𝐴 across different DP ranks. Everything is shared, and we actually get a pretty impressive performance result by running this DPEP setup. So this is we are running a DP8 EP8 on H200 node, and the model here is a Quinn MOE model, which is a pretty big 235 billion parameters, and we are running a like multi-turn chatting workload with 50 concurrent users, and each user have 4 to 5 GB 𝐝𝐞 caches. And the big thing here is the LMCache MP mode can actually achieve much better TTFD and also like higher decoding speed comparing to the in-process offload, because first of all, it has a very unified 𝐝𝐞 𝐬𝐢𝐠𝐴 pool, which means it can achieve higher 𝐝𝐞 𝐬𝐢𝐠𝐴 hit rate, and it avoids sending and receiving 𝐝𝐞 𝐬𝐢𝐠𝐴 across different ranks, so that the communication overhead can be minimized. So that is a pretty impressive benchmarking performance we see by employing this 𝐴𝐴𝐶ache MP mode. And next feature I'm going to talk about is remote storage, regarding the remote storage or multi-tier storage. So we call it like real multi-tier storage. I will explain why we call it real, but in real production, I would say it will be more and more common that KV cache will be scattered in different tiers. Like we have GPU, probably there will be some KV caches, and there will be some KV caches in local CPU or remote CPU, or maybe SSD and maybe remote storage. And during the runtime, if we want to load the KV cache for this request, what will happen? So like in the state of the art, if we are running like real-time multi-connector, it's basically a longest matching algorithm where it's trying to maximize the hit rate. But if we want to load all the KV cache into from the remote storage, you will get a very slow loading speed because remote storage will usually be very slow. And there's some other solutions, like if you're using native connectors, it will just prioritize the local CPU, and you will get very fast loading speed, of course, but the hit rate will become lower because you're just not trading off the loading delay versus the hit rate. And in 𝐴𝐴𝐶ache MP mode, we actually developed the storage controller that can send or store or load the KV cache from to those tier 2 storage at the same time. So you can actually, for the specific request, the 𝐴𝐴𝐶ache will issue load from local CPU, from remote CPU, SSD, and remote storage at the same time. It will try to look up and build a load plan and load everything concurrently into the staging buffer before it put back to the GPU. So by doing this, we can have actually higher hit rate. And also it will be fast because we are parallelly loading from multiple locations. And we're not loading a lot of things just only from remote storage, but we can we are prioritizing the trying to load as much from the faster storage as possible. So that is another very, very useful thing when doing this MP mode. And there are some slightly there are some other cool features, but I'm not going to talk about them in detail. For example, by running this MP mode, we actually significantly reduce the VRAM startup delay. So if you're using like native CPU offloading or in-process CPU offloading, it needs to a lot of time to allocate those CPU buffers, and they will be super slow. Like if you are going to allocate 200 gigs or 100, it will probably take 3 or 4 minutes. But if you're running 𝐴𝐴𝐶ache MP mode, VRAM itself does not need to allocate those page CPU or ping CPU memory at all, and startup delay will be decreased from probably 200 seconds to just 30 seconds. And by doing this MP mode, by separating the KV cache service, actually we can support this KV cache zero overhead KV cache inspection. So you can freely download the KV cache for a given request and inspect the values in it without impacting the VRAM inference at all. And also, MP mode allows you to employ this customized store and prefetch policy. You can place the, for example, if you want to place the most popular KV caches into CPU, or if you want to evict like less frequently used KV cache into second tier or slower storage, 𝐴𝐴𝐶ache MP mode will provide you an interface to do this out of the serving engine's inference cycle. So this is we also had a bunch of very cool features. Just if you're interested, feel free to check out our documents and also follow our like development on the GitHub. And the next topic I'm going to talk about is how does this MP mode help the production deployment and maintenance of your KV cache. So the first thing, talking about the production deployment, the first thing is how do we deploy this into Kubernetes environment? So we just recently released this 𝐴𝐿MCache operator or 𝐴𝐿MCache Kubernetes operator, which is available in the current 𝐴𝐿MCache repo. It's just like it's like a Kubernetes CRD, and you can plus a controller, and you can deploy the thing onto your distributed Kubernetes production cluster just via a few configuration via some kubectl calls. And if you're interested in this Kubernetes operator, you can just search for the operator in our document, 𝐴𝐿MCache document, or directly visit this docs.amcache.ai/mp/operator.html. And besides the Kubernetes operator, another very important thing in production is observability. So basically, people want to observe a lot of things regarding KV cache. So in 𝐴𝐿MCache operator, we are actually supporting 3 different levels of the observability metrics. The first one, the very basic one, is health and status monitoring. So basically, people can know, okay, what are the cache usage of different tiers, and will there be any like read and write failures happening on the second tier storage, and how many different serving engines are connected to 𝐴𝐿MCache, and whether they are healthy or not. And another category, we call it performance debugging, is basically helping the infra team to monitor the performance of all the KV cache operations. For example, we're providing this KV cache IOPS. We can also monitor the CPU to GPU transfer speed, and also we can export this IO throughput and latency as well. And third, which is I would say is actually becoming more and more important, is that the production insights. So those will include, for example, KV cache hit rate, showing that how many requests are hitting KV cache into your in your current production deployment. And also, 𝐴𝐿MCache will can support monitoring the KV cache lifecycle in different tiers. Like for example, how long does this KV cache stay in CPU? How long does it stay in disk? Those kind of things. And we actually we can actually support this time between eviction and reuse, telling you that okay, now your storage is not enough. You probably want to increase your storage by X% to improve the cache rate by Y%, something like that. And all those observability metrics will be exported via Prometheus and OpenTelemetry interface, very standard. And if you have, for example, Grafana or Datadog, all those kind of things, it can be directly plugged into your production system. And another very important thing in production is fault tolerance. So nobody want their service being down just because of 1 or 2 runtime errors in some of the modules in the system. So by using 𝐴𝐿MCache MP mode, we are actually having this two-way of fault tolerance. First of all, when you shut down the VM or the VM dies due to some kind of runtime errors, the 𝐴𝐿MCache MP process will still be there and will still keep operating the KV cache on CPU and storage, which means that when you shut down your VM, you will not lose your you will not lose all the KV caches stored in CPU, and all those KV caches can be readily reused by other VM engines that is still alive. And on the other hand, if there's anything wrong with 𝐴𝐿MCache process, actually we already have the functionality to make sure that it does not break VM. So if the 𝐴𝐿MCache process becomes unhealthy, the VM process will automatically detect that and entering the downgrade mode. In this downgrade mode, the KV cache the 𝐴𝐿MCache functionality will be temporarily disabled, but the VRM itself will still be capable of doing normal inference. And once we restart the 𝐴𝐿MCache process, VRM will try to reconnect when 𝐴𝐿MCache comes back. So that is fault tolerance part of the 𝐴𝐿MCache MP mode. And we also have this 𝐴𝐿MCache CLI, basically helps you maintain the 𝐴𝐿MCache servers or trying to inspect the statuses in the 𝐴𝐿MCache. So we have this 𝐴𝐿MCache server. It will help you launch the 𝐴𝐿MCache MP mode locally. We have this 𝐴𝐿MCache describe, which is pretty much the same, pretty much similar to kubectl describe, where you can describe your engine connections and storage status and a lot of details inside 𝐴𝐿MCache. And we have 𝐴𝐿MCache ping and 𝐴𝐿MCache query. You can do basic health checks, and you can run simple queries and measure performance and see whether it's expected or not. And something we will release very soon is we call 𝐴𝐿MCache trace, which will tracing the I/O operations in 𝐴𝐿MCache for future replay. If you want to debug your storage system, if you want to debug your system performance without running VRM, 𝐴𝐿MCache trace and 𝐴𝐿MCache bench will be a very useful tool to help you trace the operations, print the traces, and replay the traces to debug the performance. So that part is our CLI tool, and most of them are available, and feel free to check out the documentation as well. There's a page describing all the CLI tools. And I'm also very excited to share this MP mode development roadmap, what we have already done and what are the upcoming items. So the MP mode actually started late 2025, late last year. By then, we are doing just CPU sharing and zero copy optimizations and Docker deploy. And earlier this year, we are adding storage support, Kubernetes operator, error handling, 𝐴𝐿MCache CLI, all those kind of features into 𝐴𝐿MCache MP mode. And also, regarding research advancements, probably some of you already know we have this cache blend, which enables non-prefix KV caching, that you can reuse the KV cache not only for the prefix, but also for non-prefix. And the upcoming items, we are actively working on this RDMA distributed sharing. We're also working on GDS support. And later this year, there will be storage optimizations, pluggable storage policy, global KV cache management, all those kind of interfaces. And on the research side, there will be KV cache compression. You know, TurboQuant is super hot, and we have done a KV cache compression algorithm like 2 or 3 years ago called CacheGen. And there will be like smart KV cache editing that will be put into 𝐴𝐿MCache as well. And finally, before the end of my talk, I also want to share a little bit more on the 𝐴𝐿MCache long-term vision. So people I would say it's become more and more common that people realize that the KV cache is a game changer. So KV cache, it's people could see it as the intermediate compute states. Therefore, by just reusing the KV cache, we can skip the compute and reduce delay. But actually, KV cache is more than that. KV cache also captures large language models' internal understanding of the context, which means that it can be approximated while it still preserving its semantics. That's why those compressions, those non-prefix reuse can make sense. And also, the KV cache will directly impact the large language model's output generation, which means that if we can manipulate KV cache a little bit, we can control like how large language models pay attention to different tokens and directly impact the inference output accuracy. We can do a lot of things there on the KV cache. So our understanding of our perception about KV cache is it's not only just tensors, it's not only just cacheable items, but it's actually the AI native data for the future, for for the future, as long as the transformers is still prevalent. And there's actually a lot of ideas in this literature. Like the research community is going very, very fast. So I would say recently nowadays on the industry side, it becomes more and more common that we all those like plumbing work, like page attention, CPU offloading, remote storage are already done. But on the research side, on the academic side, there's a lot of KV cache optimizations yet to be adopted by the production, by the industry. Like KV cache compression, people are starting to try that. We have this blending, we have partial reuse, semantic reuse, cross-model reuse, or even manipulating the KV cache content to achieve better output quality. So by doing 𝐴𝐿MCache, our long-term vision is that we want to make 𝐴𝐿MCache a platform to bring all those latest research ideas to fancy KV cache optimizations into production. Like people can land, test their ideas and land that into production, and the industry people will be able to benefit from all those latest advanced KV cache research by using 𝐴𝐿MCache very easily. So that's a long-term goal of I say that's a long-term goal of 𝐴𝐿MCache. We want to build this best AI native data plane. And if you want to know more details about the MP mode, just feel free to visit our documentation website at https at docs.amcache.ai/mp. And that's all for my today's talk. And feel free to let me know if there are any questions.
Thank you very much, Yihua. This was a great presentation. I don't see any questions yet, but let's give it a minute to see if people want to formulate something. Feel free to ask your question either on the chat or just unmute yourself. That works too. Really, no questions? Maybe you went into too much detail and you answered all the questions.
Probably people, I'm not sure. Probably I talk too much technical stuff. I mean, just feel free to reach out on the Slack channels as well. We are happy to answer any questions if you have, and also feel free to try MP mode and create issues or PRs if you are interested. It's super welcome for you to try it and let us know if you met any issues.
All right. I guess that concludes this meeting. Thank you very much, everyone, for joining. Very well done, Yihua. And we'll be having the next meeting on a Wednesday, starting next month. The office hour is going to be on Wednesday to avoid conflict with other projects.
Thank you, guys. See you.
Thank you.